Have you ever stopped to think about how the massive amount of power humming across the national grid actually gets into your home, safely and reliably? Well, the answer is hidden in plain sight, inside facilities just like this one, a modern electrical substation. They're basically the silent, powerful hearts of our cities. So what's really going on inside one of these complex, high-voltage hubs? Let's peel back the walls and take a look.
All right, we're going to take a bit of a virtual tour. We'll start right where the raw power arrives. Then we'll move into the high-tech control center. After that, we'll explore the station's brain, uncover its hidden life support systems, and finally, we'll see how this whole thing comes together, from a simple blueprint to a living, breathing reality.
Okay, so our first stop is outside in what's known as the transformer yard. This is the front door. It's where the raw, super high-voltage electricity coming in from the transmission lines begins its incredible transformation into a voltage that we can actually use in our neighborhoods.
And the star of the show out here is the power transformer. You really can think of it as the beating heart of the entire facility. Its main job, its whole purpose, is to take that incredibly high voltage, we're talking 115,000 volts, and step it way down to a much more manageable 13,800 volts that can be sent out into the city.
Now, this isn't just a simple box. It's packed with sophisticated tech. It has something called an on-load tap changer, or OLTC, which makes these tiny, constant adjustments to keep the voltage perfectly stable. It has advanced cooling systems, basically giant radiators, to deal with the incredible heat it generates. And, most importantly, it has what's called differential protection, which is like a super fast emergency stop. If it senses an internal problem, it shuts everything down in a fraction of a second to prevent a major failure.
So the big question is, how do you get 115,000 volts from that transformer outside safely into the main building? The answer is this, a gas-insulated bus duct. You can picture it as a super secure, high-pressure insulated highway for electricity. It's the critical bridge that channels all that raw power indoors.
And now we head inside the building, into the GIS hall. This room is the reason modern substations can exist right in the middle of our crowded cities. This technology is a real game changer when it comes to saving space. And this is it, GIS, which stands for Gas Insulated Switchgear. It's a totally sealed metal-enclosed system. All the critical high-voltage parts, the breakers, the switches, you name it, are housed inside, surrounded by a special insulating gas called SF₆. The biggest advantage here? It shrinks the physical footprint of all this equipment down to a fraction of what it used to be. It's kind of amazing.
So what does it do? Well, the GIS is basically the high-voltage traffic cop. It uses circuit breakers that operate at lightning speed to protect the grid and isolate any problems in milliseconds. It also has these tiny, super precise transformers built right in to constantly measure the electricity flowing through it, feeding all that data back to the brain of the substation. It's really the first line of both defense and control.
You know, to make sure all of this is incredibly safe, engineers do these mind-bendingly complex calculations. One of the big ones is the short-circuit current analysis. What they're doing is simulating the absolute worst-case scenario, a massive electrical fault, to prove, with pure math, that every single piece of equipment can take that hit without blowing apart. It's this kind of proactive engineering that makes our power grids so reliable.
Okay, so once the power has been stepped down and managed by the GIS, where does it go? It goes right over here, to the 13.8 kilovolt Metal-Clad switchgear. So if the GIS is managing the high-voltage superhighway coming in, this switchgear is managing all the medium-voltage city streets going out. It uses regular air for insulation and has rows of individual circuit breakers, each one protecting a specific feeder line that powers a neighborhood or a big factory.
We've seen the muscle of the substation, right? The heavy-duty hardware. Now let's go check out its central nervous system and its brain, the control rooms, and the incredible network of cables that's hidden right underneath our feet.
Welcome to the command center. These panels are filled with what are called protective relays. They're basically specialized computers running complex logic that automatically detects any hint of a problem on the grid. And through the SCADA system, engineers, who could be hundreds of miles away, can remotely monitor and control every single switch in this entire building, all connected through a super-fast fiber optic network.
But you know, the real unsung hero of this whole operation is right under the floor. It's the cable basement. And this isn't some messy, dusty crawl space. No way.
It is a perfectly, meticulously organized highway of thousands of power and control cables running on dedicated trays, connecting every single piece of equipment back to the control room's brain.
So what happens if the main power grid goes down and the substation itself loses power? I mean, that's a great question. And that's exactly where the hidden life support systems kick in. These are all the background services that guarantee this place can do its job no matter what's happening outside.
The key word here is redundancy. This station has its very own AC and DC power systems, complete with massive banks of batteries and uninterruptible power supplies, or UPS. This keeps the control systems and computers online even during a total blackout. On top of that, you've got powerful HVAC systems to keep all the sensitive electronics cool, plus advanced fire suppression and security systems to protect the whole investment.
So for our final stop, how does a place like this go from just a set of drawings to a critical, fully operational piece of our power grid? Well, it all comes down to two major things: absolutely rigorous testing and an almost unbelievable amount of materials. Before a single customer gets power from a new station, it goes through this exhaustive process called commissioning. It happens in two stages. First, you have the primary tests, where they apply high voltage to the big stuff, the muscle, to make sure it's physically sound. Then come the secondary tests, where they check every single wire, every protection setting, every control signal to make sure the brain is talking perfectly to the muscle.
And when I say rigorous, I mean it. Every single connection is verified. Technicians will literally inject fake signals to simulate faults, just to watch and make sure the right breakers trip exactly when they're supposed to. Absolutely nothing is left to chance. Safety and reliability are proven right here, long before the station is ever switched on for real.
If you want to get a sense of the sheer scale of one of these projects, all you have to do is look at the bill of quantities, or the BOQ. This is the master shopping list for the entire project. You can see it's broken down into 4 huge categories: civil works, like the building itself, the core; electrical equipment, the mechanical systems, like HVAC and all that auxiliary support infrastructure we just talked about. And to give you just one example of the complexity, let's look at one line item from that electrical BOQ: control cables. A single substation like this one can require up to 40 kilometers of control and communication wiring. I mean, think about that. That's enough cable to stretch clear across a small city, and it's all tucked away neatly in those basement trays.
So, after our tour, what are the big takeaways? Well, first, that amazing GIS technology is what makes these compact urban substations possible. Second, the transformer and switchgear are the real workhorses, doing the heavy lifting of converting and distributing power. Third, the control and auxiliary systems are the vital brain and life support. And finally, none of this goes online without that meticulous testing, which proves the quality of a project with an absolutely immense logistical scale.
And all of this leaves us with one final, big question to think about. Our world is electrifying faster than ever before. We've got smart grids, renewable energy, and electric vehicles changing the entire game. So as our power demands continue to grow, how will the design of these critical power hubs have to evolve to meet that challenge?